we're going to talk about systems of equations. We're going to start with two equations, two variables. So first thing I'm going to do is define what a system is. Okay? So this is a really simple idea. System of equations is just when you have two or more equations. Two or more equations. So actually a system can be very simple or very complicated. The ones we're going to start with are very simple, but usually we use a little bracket to sort of collect all the equations, and it's a one-sided bracket. So you have this little bracket, and then you might have like 2x minus 6y equals something, 4x plus y equals something. Okay, so let's say that this is negative 34 and negative 3 or something. Okay? So this is considered a linear system because these are actually lines. They're both lines. But you could have quadratic systems too, like conic systems. You could have two hyperbolas. You could have three hyperbolas, right? The goal is to actually kind of see where they cross. So if you see the verb solve, solve means to find the point of intersection. So this word, for example, in this system would mean go ahead and find where the lines cross. Like where do they cross? So the solution to the system is an intersection point. Which means you're going to have to write your answers in ordered pair form. So your answers, so therefore, your answers should be written as x comma y. Okay, so this first slide is very simple. System just means two or more equations. Solution means to find the point it crosses. So solve means find the point it crosses at, the lines cross at. And then your answers should be written as ordered pairs because they're describing a position of crossing. See? Okay, now, there are three possibilities in the world of two dimensions. There's only three possible drawings, okay? So in our first drawing, we have two lines that actually do cross. Okay, so you have one solution. Okay, or you can have two lines that are the same line. So this happens, it's rare, but it happens. So I tried to draw a blue and a purple line actually physically together. Okay? And so if I said solve the system, technically there are many solutions. Every single point is technically a place of intersection. So there are infinitely many solutions. In this diagram. And then there is a third drawing. There's technically a third case where the two lines don't cross at all. Okay, so let me draw the third case. Of course, that'd be just two parallel lines in Euclidean space. Okay, so two lines that do not cross, so no solution. So geometrically, there are only three possibilities in the world of two lines on a plane. Okay? So if we're on a flat plane and we draw two straight lines, only one of three things can happen. Either they cross, or they don't, or they're the same line. There's no other possibilities. Now, if you live on a sphere, that's not true. Actually, we do kind of live on a sphere. If you think about a spherical world where you're not allowed to draw off the surface of the sphere, so you don't have to draw this, but just bear with me for a second. Let's say you have a sphere. Okay? When you try to draw lines on a sphere, you're actually supposed to draw them in such a way that they encompass the center of the sphere as the center of your drawing. So basically, a straight line on a sphere is defined as that. So that would be, for example, a straight line on a sphere. The reason it's straight is because every pilot knows when they're flying around the Earth, right, that if they start in one city and they want to fly to another city, the shortest possible path is to follow a path like this one. It's actually a circle to our eyes, but to the pilot, it's the straightest shot they can make. They can't fly off into outer space, like tangent to the Earth, right? They're trying to stay in the atmosphere, so they travel along what's called a great circle. So to us, it looks like a circle, but to the pilot, they're flying in a nice straight line. Okay? Pilots who fly on these lines save gas for their planes. If a pilot tries to deviate from the course of this line, they will actually be wasting fuel. So this is the best, shortest possible route between two cities on the globe, is to follow a great circle. You'll notice that if I draw another one, right, I cannot even do it in such a way as to avoid contact with the red. It is impossible to draw two lines on a sphere and not have them cross. There is no such thing as parallel lines on a sphere. No matter what I do, the red and blue cross, and they not only cross once, but twice. One's in the front of the Earth here and one's in the back. There's nothing you can do about it. This is the world of spherical geometry, where rules are a little different. There are no such thing as parallel lines. Interesting. So all solutions have a system. All systems have a solution, not just one, but two. There's actually two contact points for those two lines. Question?
What if your line isn't rotating around the center of the sphere?
Okay, that's a good question. That's a very good question. So, on the Earth, we have lines of longitude. You guys have heard that word before. Longitude. Oops. That's a bad drawing. All the lines of longitude have one thing in common. They all pass through the poles of the Earth, right? Specifically the North Pole and South Pole. They all intersect at Santa Claus's house at the top of the Earth. They also all intersect down at the South Pole, right? All lines of latitude intersect. But there are these things called lines of latitude which appear parallel. Isn't that true? The lines of latitude, here's the equator, but there are other lines of latitude that wrap around the Earth like this, and they appear to be parallel. Didn't I just say there's no such thing as parallel lines on a sphere? I thought I just said that. I did say that. Those aren't lines. The only one that's a line is this one. These are circles. All the rest of these are circles, not only to your eyes, but also to a person traveling the Earth. They're not straight. Pilots don't fly on them. You waste fuel. You actually, if you're flying a plane along a line of latitude other than the equator, you actually have to turn the wheel to stay on course. If you're flying on the equator, you just take your hands off the wheel. Fly straight. Okay, the pilot could actually do this and fly on a great circle. But to stay on one of these other red lines, they have to actually hold the wheel. That proves it's not a straight line. Okay? So to answer your question, it's not a line. Okay? There is no such thing as parallel straight lines on a sphere. But of course we're in the Euclidean world, and everything is perfectly flat. So we do have the parallel case here. Right? There are also hyperbolic geometries, and in the hyperbolic geometries, the opposite is true. You can have plenty of parallel lines passing through a given point, and they're not the same line. So that's a very interesting phenomenon. If you want to come in sometime, we could talk about saddle geometry, and that would blow your mind. I promise, it'll blow your mind. Beautiful stuff. We're in the simple world of two-dimensional Euclidean geometry. Straight lines either cross or they don't, or they're the same line. Everyone with me here? Okay, so you can ignore what we said about the sphere. That was just for fun. I know some of you like that kind of thing. All right, let's go to a specific case of a system. So I'm going to use the same example in every problem, but we're going to solve the problem 6 different ways. Okay, so let me grab my example from earlier. I like this example. Okay, so let's go ahead and steal that example. All right. So the first thing you can do is you can just solve by graphing. Okay? So to solve by graphing, of course, you graph the lines. You might want to put them in y equals mx plus b form first. That will help you get things organized. So y is equal to 1/3 x plus 34/6. That's the first line. Okay? And the second line is y equals negative 4x minus 3. Okay, so for our first line, it has slope 1/3, and it passes through, it's about 5.5 roughly, not exactly, but close. And the second one, the y equals negative 4x minus 3, that one obviously passes through negative 3, and has a slope negative 4/3. Draw a line. Let's do a blue line again. Okay. This is the other one. The goal was to solve the system. The solution is this point of intersection. Where is that? Maybe negative 2,5 maybe? Tough call. Why is this a bad method for solving? Yeah, this trusts 2 things. It trusts your art skills and your eyeballs. Okay? It trusts your art skills because you have to draw them very, very carefully. It trusts your eyeballs because after you draw them, you have to check really carefully to see where they cross. Think this is a pretty good method?
Oh, yeah.
Pretty bad method.
It's a great
Okay? Another method is substitution. So the theory on substitution is, of course, look, if they're the same, if they're going to cross at the same point, then we can assume that where they do cross, their y values match. So you would just take 1/3 x plus 34/6 and set it equal to negative 4x minus 3. See? That's a pretty good thought. Maybe multiply everything by 6. Right? That way it reads 2x plus 34 equals negative 24x minus 18. You could bring the x's to one side, bring the y's to one side, and divide. Hey, we got x equals negative 2, and we did not have to eyeball it. That's a better method, isn't it? It's just more accurate. I mean, I trust it a lot more than the previous solution. How are you going to get the y coordinate having found the x coordinate? Plug it in, right? So plug in your x to get your y. So 2x minus 6y equals negative 34. Y is 5. You get the same answer, but you don't have to trust your eyeballs. It's called substitution because we substituted one equation for the other, and in the end we also substituted to get our y, right? Okay, do you see any drawbacks to this method? The first one trusts your art skills and your eyeballs. Is there anything iffy or awkward or difficult about method 2 here? What? You did have to isolate y. The truth is you don't have to isolate y in both equations, but you have to, at least in one equation, isolate one variable. Okay? If you were teaching a computer to solve this problem, how would you teach it to isolate y? If you're a computer programmer, how do you teach a computer to isolate a variable? That's an interesting question, isn't it? So this just might not be the go-to for a person programming their calculator to solve a matrix, or solve a system, okay? They'd probably use something like matrices or something, where you don't even have to write x and y. Okay, so these are two methods, both sound, but especially that second one, both with their own little drawbacks. Let's go on to the third method. And it's not like these methods get better and better and more efficient and more efficient. It's just they're different methods. The first one is just kind of the only one that's really bad. Okay, let's look at elimination method. You know this method. So in the elimination method, the idea is, listen, I'm allowed to add equations whenever I want. Maybe there's a way I can sort of add them to get what I want. Right? Okay, so let's see here. Let me add these equations. 6x minus 5y equals negative 37. Is that the elimination method? That is not the elimination method. That's called adding two equations randomly for fun. However, even though this is a complete waste of time, it has a name. It's called a linear combination. A linear combination. So let's at least title this, even though it's a complete waste of time what we just did. When I was in college, I took a linear algebra class. My professor used this word over and over and over and over again. Linear combination, linear combination, linear combination. And I didn't know what it meant, because my teachers in high school never told me. So then I had to go and look it up. It took me a half hour to realize what the teacher was saying. You know what the teacher was saying with the word linear combination? She added 2 lines. But it took me a half hour to figure that out. So I just added 2 lines and I got a linear combination. Okay, I wanted to tell you that before you got to college. Okay? Before you get into the real vocabulary of matrix algebra and stuff. Okay? So just know the linear combination just means you added 2 lines. Notice that was kind of a waste of time. So let's try to get our linear combination to have only one variable. Okay? So let's be wise about this. Why don't we multiply the second equation by 6? Why is that better? Yeah. This will actually accomplish something. It will make a linear combination with one variable, right? Okay, let's give it a try. We're really doing 2x plus 24x, of course. There is no y, beautiful. And we have really negative 34 plus negative 18, so negative 52. Here we recover that x equals negative 2 solution we had earlier. And we can get y by substituting, of course. We can still get our y equals 5 later. But this method is finding a linear combination that has one variable. Okay, so I'm sort of upping the ante on the vocab here. It's not let's get rid of a variable. It's let's find a linear combo that has one variable. That's a nice way to solve. The pluses of this method, the pros, the good side of this method, is that we didn't have to isolate anything. The bad side of this is they do have to be lined up perfectly. Like you have to have the x's on top of the x's, the y's on top of the y's, and so forth. But normally that's how they're given anyway, right? Okay. Any other drawbacks or maybe potential mishaps? Any reasons why this method might fail us someday?
If your coefficients suck.
Yeah, sometimes the coefficients are just bad, like 3/34ths and 9/16ths, and that's just the first equation.
If you have like 3 variables, it's hard to solve for, get to the whole thing.
You're right, this is really hard in 3 variables. I will say, though, it is better than the other previous methods we've seen today. So unfortunately, if we have 3 equations and 3 variables, this is still the fastest of the ones we've seen so far. But you're right, it is hard with 3 variables.
Do we want to substitute and eliminate?
I never use substitution on anything higher than second dimension. I don't use substitution ever anyway, unless I'm doing non-linear curves. So like if I'm setting a parabola equal to a hyperbola, I might use substitution method a lot. But elimination is really the way to go. This is the preferred method of most students, and it does have very few pitfalls. Occasionally you do get 0 equals 0, but that has meaning. Okay? It's actually the all real numbers case. Sometimes you get something goofy like 0 equals negative 52. But that has meaning. It just means that you have no solution for that system. It's an inconsistent system. But the other possibility is matrices. So the next method I'm going to show you are the matrix methods. There are 3 matrix methods I want to teach you. Row reducing, Cramers Rule, and matrix inversion. 3 methods for matrices. So there's 3 more ways coming here. I don't think I'll make it to matrix inversion today. But it doesn't matter, because your worksheet doesn't have that on there anyway. All right, so the next one is to use matrices. So the first thing you know is we would probably write this problem like this, actually, in the matrix world. There's more than one way, but this is called an augmented matrix. What it really is 2 matrices combined. The left side here is called the coefficient matrix. And it is being connected or augmented to this matrix on the right, which I usually just call the right side matrix. I've never seen anyone really give that thing a name. Okay? So this is an augmented matrix, the whole thing. The left side is the coefficient matrix, the right side is the right side matrix. And the little dashed line, of course, is representative of our equal signs. So this is still the same exact problem in disguise. It really just means 2x minus 6y equals negative 34. So in a way, this little dashed line is like your equal signs, right? And then the fact that the 2 is in the first space means it's your x's. So we're not writing x anymore. We're just putting it in the first space, which means it's 2x. Okay? So this is a little less writing, I guess. You're not writing x and y at least. And if this was a system of 10 equations and 10 unknowns, it would be a lot less writing. You would never have to write x or y or equals. You just do the numbers only. So it's kind of an efficiency thing, making it less work for us. But remember what we did with the elimination method. We can apply that here. Okay, so as you know, these are called the rows. And here are the things you're allowed to do. You may multiply any row by a number. So you may multiply any row by any number except 0. Don't multiply by 0. You'll ruin the whole problem. Okay? Please don't multiply by 0. The second thing you're allowed to do is add any 2 rows. Go ahead and place your resulting sum in either row. And the third thing you're allowed to do is switch any 2 rows. Now let's talk about why these rules are allowed. Remember what these rows mean. What are the 2 rows I circled there, the 2 red rows? What do they represent? They just represent the old equations. So for me to say that you can multiply a row by a number is the same thing as me allowing you to multiply an equation by a number. No harm, no foul. You can do that. Just don't multiply by 0. Adding 2 rows together. Why is that allowed? Well, you're allowed to add equations, linear combination. So you should be allowed to add rows. The rows are the equations, right? Switch 2 rows. Can you imagine a teacher who's so strict they wouldn't let you trade your 2 equations around on your piece of paper? You may not write that equation on top. I had it underneath the other one. You can't switch them. I bought the paper, it's my pencil. I bought it at Staples, I bought this piece of paper, I can write the equations in either order, thank you very much. Right? So for me to allow you these 3 freedoms, with rows is the same thing as for me to allow you to use 3 freedoms with equations. So these are not mysterious. Of course these are allowed. There's nothing mysterious about them. No truths would change if we did these 3 things. So now let's solve this problem, okay? Using row reduction. So this is called rules of row reduction. Rules of row reduction. Oh, and let me tell you our goal here. Our goal is we want to transform the augmented matrix A, B, C, D, E, F. We can use these 3 rules. We're trying to get it to look like this. 1, 0, 0, 1, x, y. By applying the 3 blue rules, our goal is to transform the augmented matrix to look like this. A couple more vocab words here. The left side is called the identity 2 matrix. This is the identity matrix with dimensions 2 by 2. And these are just your solution to the problem. Like when you're done transforming, your answers for x and y will be chilling on the right. They'll be waiting for you to circle them. Okay? So let's give this a try. This is called row reduction. Alright, here is the problem. Here is the augmented matrix version of it. A little less writing. What am I allowed to do? Well, I'm allowed to add rows. My goals are always the same. I always want to get a 0 here. I want a 0 here. How am I going to achieve that? Well, I could multiply my first row by -2. That'd be a good starting place. It's a good first step. Why is that a good first step? Now I have a 4 and a -4, one on top of the other. Then I can add these together. Now I get to place my answer, which is 0, 13, 65. I get to place this resulting sum in either row. My goal was to get a 0 in the lower left. So I'm going to place those 3 resulting sums on the bottom row. So I'm going to leave this as -4, 12, 68. But this row officially reads 0, 13, 65. I will then multiply by 1/13 on this bottom row. And this leads me to the augmented matrix -4, 12, 68, and 0, 1, 5. I've accomplished half my goal. I was trying to get 0 and 1 on the bottom row there, and I did it. Okay, my next goal is to get a 0 here. So I'm going to now multiply the bottom row by -12. By the way, your work and my work might differ at some point, and we might choose to do different things. But our goals are the same. It's like 2 people might solve Rubik's Cube, but with slightly different algorithms. Now I'm going to add these 2 together. This time I'm going to place my answer along the top. -4, 0, 8. I'm going to leave that bottom row as is. For my last step, I'm going to go ahead and multiply the bottom row by -1/12 again, and the top row by -1/4. Here's my answer. 1, 0, -2, 0, 1, 5. The solution to the system is chilling on the right. There it is, -2, 5. How do I know this is the answer? The left side is the identity matrix. Now you might say, Mr. Shore, that's pretty neat, but that was a lot of work. Well, this might be your faster method in 3 dimensions. Okay? All right. Once you have this all done, this is called reduced row echelon form, or I like to call it RREF. I'm not the only one who actually calls it that. You can tell it's in reduced row echelon form when you have identity on the left, solution on the right. And the method is called row reduction, and there's some other names for it too, unfortunately. That probably won't be your favorite method, but in 3 dimensions it might be. I have one more method. Jack?
Oh, I was just gonna ask you, what's
Uh-huh.
the purpose of things like 4x4 and 5x5 matrix? There's only
When you have 5 unknowns and 5 facts about them, and you need to know what those unknowns are. You can set up a 5x5 matrix. Okay, the last method is Cramers Rule, also one of our matrix methods. And I'm getting slim on time, but I think I can pull it off, and if I can't, I'll just finish the recording 6th period. Make sure you watch it. Your worksheet does include one Cramers Rule problem. Okay, so Cramer was a complete genius, and he figured out how to just manipulate these 6 numbers to get the answer. Okay? So Cramer basically figured out that if you do this, I'll show you using letters. Here's what he said. Basically, he said that if you have A, B, C, D, and this side says E and F, you can actually find X by dividing D sub X over D. Now, D sub X is just the determinant A, C, sorry, I wrote that wrong. It's E, F, B, D, and capital D is just the determinant A, B, C, D. Okay, so here's what he was saying. He's basically saying if you want to find X on this problem, go ahead and write your augmented matrix if you like. Here's your augmented matrix, right? You can find X lickety-split really fast by doing this. Negative 34, negative 3, negative 6, 1, determinant, over 2, negative 6, 4, 1, determinant. Now you guys remember how to do a determinant? You just kind of cross multiply and subtract. That's a negative 34. So the top comes out to negative 34 minus 18. Negative 52. And then on the bottom, you do the same little cross multiply trick. 2 times 1 minus 4 times negative 6. And this comes out to 2 plus 24, which is, of course, 26. Look at that. Bam, you got the answer for X right there. And he also had a way for you to find Y. You could probably guess what it is. This is the method to find X. This is how you find X up here. Okay? Does anyone remember, or can you guess how you might find Y? Yeah, it's called D sub Y over D. The top has the A and the C here. The E and the F go here. The bottom is the same. So let's go ahead and try that. So Y is going to be these two determinants. The bottom's the exact same one. So this is just going to end up being 26 on the bottoms again. But the top's a little different. This time we have the negative 34 and the negative 3 here. See? So your cross multiplying looks a little different on the top. So we have 2 times negative 3 minus negative 34 times 4. The bottom is exactly the same problem as before. Maybe you remember doing this last year. It was supposed to be in your curriculum. So the top is basically negative 60, negative 6, and you're adding 68 times 2, 136. The bottom is just 2 plus 24. So what's 130 over 26? Fine. Now if you're programming a computer, right, this is actually kind of a nice way to program the computer because the computer already has, you're actually already telling it what to do with all the input coefficients and how to actually get x in one step. So the calculator would just have to know the algorithm for determinants to solve this, you see. But it's the same answer, negative 2, 5. And so what's that? 6 methods. We got graphing and substitution, elimination, matrix row reduction, and Cramers Rule. And there's one more that's inverse matrix method. But actually it kind of makes sense to save that for another day. So here's what your worksheet sort of looks like. See if I can find it here. It's one problem for the weekend, okay? You're going to solve it by all 5 methods. Bonus if you can figure out the matrix inversion method. Or just look it up online and try it. Bonus points there. Okay? Have a good weekend.